Hello and welcome to this workshop on what is epistemic inquiry, how is epistemic inquiry taught. We'll look at the three worlds of Karl Popper and his view of the nature of science and use some of those ideas to help design a teaching sequence and a unit design for genetics and evolution for grade 8 teachers. So what is epistemic inquiry? Well, it's based on the four big questions about the nature of science that Kind and Osborne put forward. The idea of what exists, how do things happen, how do we come to know, and what can we do or what should we do with this knowledge. A large part of the methodology of this, the way this epistemic inquiry is taught, comes from the cognitive acceleration through science education, otherwise known as CASE, which has 5 pillars of designing lessons and designing learning sequences that start with some form of concrete preparation that often then leads to a situation where we elicit views from students about a phenomena or about some thinking about phenomena, and then we create cognitive conflict, which gets the students to often make predictions which then will be different, or explanations that are different, and then this often leads to some very fruitful discussion in a process we call social construction. A major part of epistemic inquiry is the concept of metacognition, where we're constantly thinking about the knowledge we think we have, the thinking that we have, and so we monitor and plan and evaluate how our thinking is going, how it relates to the evidence that we're dealing with, how sound our arguments are. And a final part is the type of thinking that we're doing, the creation of scientific models, the concepts of inference from observation, the kind of issues that we bring in, the scientific processes that we try to bridge in other lessons and in other units, so that science is built up as a process of thinking inquiry that is applicable across a wide range of phenomena. You'll see that in these lessons that we're going to look at. The three worlds of Karl Popper, the idea that there's physical objects, or what in the NGSS they refer to often as phenomena, and our subjective experience of them. In particular, we know that learners bring prior experience or prior ideas or ways of thinking about the world, that they use their senses, that this subjective experience needs to be refined into the kind of objective knowledge that we're trying to build up in scientific inquiry. Models, argumentation, good theories, data analysis. And you'll see that a large amount of language is used in trying to build up this picture. So we're going to apply this genetics and evolution through epistemic inquiry. We're going to start with a very interesting phenomena of twins who are very diverse. Pedigree charts and phenotypes will be used to try to explain some of this phenomena. We'll look at the issues that Mendel wrestled with about whether the widely held belief that offspring are a blending of characteristics of their parents, and so a blending theory of inheritance, as opposed to a particulate theory, which is what he moved towards. And we'll see how the development of models like Punnett squares and the idea of genotype was used to try to explain a lot of the observations of genetics. Then a second phenomenon very interesting about how black wolves developed within grey wolf populations for what we believe to be hybridization with domestic dogs and a dominant allele that produced melanin to turn the wolves black, we'll look at concepts like the gene loci and genotype to explain this. And then we'll see that the geographical distribution of these black wolves in North America and in northern Italy in particular tell us a lot about the role of natural selection and the way genetics is bound into that. So the first interesting phenomenon we're going to use to kick off the lessons to do with genetics and then later evolution, a family in the UK, and you'll see we call it diverse twins, and we're going to use this phenomena to introduce the idea of pedigree charts and phenotypes. And then later we'll look at some of the work that Mendel did, and in particular he wrestled with the evidence for a blending concept or a particular model of inheritance and the use of Punnett squares. So let's start with, this is a photograph of a family. Some basic information: the two adults are the biological parents of the 5 children. That's important that you know that, so you don't say that some of them might be adopted or just brought in for the photograph. So the first thing to do is, with your fellow teachers, to look at the photograph and see what you observe, and from your observations what you might infer. This is using the idea of what exists, because this is very, very important at this stage to get clear the kind of phenomena that may well be very clearly genetic, those that are absolutely not genetic, and those that might be somewhere in a grey area having genetic components. Also, think about what you think your students would focus on. What kind of things would they observe and make inferences about? And then the question is, how would you as teachers guide the ideas that they bring out from this phenomena? Then we move on to a practical activity. Once you finish those discussions and probably on a board or somewhere recorded their ideas, we look at how we use the model that is shown by pedigree charts to actually organize this. And here is a blank pedigree chart, and I would let the students organize and sort and justify the way they've sorted them, and also again what exists in this pedigree chart. We have certain symbolisms and a certain structure that show the existence of certain things that are not obviously observable, but are more inferences we make. So I'll give you some time to do that and think, how would you guide your students? How much guidance would you give them? It might well be that they spontaneously ask, what's the difference between the squares and the circles? I would ask them, well, if you count some of the individuals, you should be able to make your mind up for that. Then you can check for understanding and again highlight the features of the pedigree chart and what it tells us, the idea of generations existing, the idea of offspring, and the idea of being siblings could well come out. Then we're going to focus on 2 of the girls. This is later than the initial photograph. And watch this short video, and then after that there's an opportunity to discuss what did you observe about the discussion in the video. It's not a scientific video, it's more of a social news kind of video. And what kind of things do you think your students would want to ask or would comment upon.
These pretty teens are best friends, and they're also something else. Something that may surprise you.
We're twins.
Believe it or not, they're twins.
Yep, we're twins. We're
twin
mum,
sisters.
same dad.
You heard right. They have the same mom and dad. What are the odds that one would be black and one white?
A lot of people are just in shock.
Lucy and Maria Aylmer live in Gloucester, England. Maria has a caramel complexion, brown eyes, and thick curly black hair. Lucy has pale white skin, ginger red hair, blue eyes, and freckles. Most people have the same reaction when they hear they are twins.
They say, how did it happen? We don't believe you.
So, how did it happen? Their mom, Donna, is half black and half white. The twins' dad, Vince, is white. The couple was thrilled when a sonogram revealed they were expecting twins.
I just cried. It was shock.
Mom did a double take when she delivered one black and one white baby.
I'm so glad Mum dressed us in such cute little outfits.
Mom dressed her adorable twin daughters in matching outfits, just like twins everywhere. But by age 10, Lucy says she didn't feel like a twin, so why dress like one?
We don't look alike, so why should we have to wear the exact same thing?
Maria says she once wished for Lucy's straight hair.
I used to cry about it. I hate my curly hair.
And Lucy says she was sometimes taunted at school.
They thought I was adopted and calling me a ghost.
Now 18, the twins not only look different, they have very different personalities.
We're completely different.
Maria loves getting dressed up in chic clothing. She is very outgoing.
I love meeting people. Like, I'm not scared to approach people or anything, so.
Whereas I'm terrified of going up to random strangers.
Lucy prefers casual clothes, but they've come to embrace their uniqueness as black and white twins.
If I have kids one day, they might come out looking like Lucy.
So we've already discussed some of the things that exist in pedigree charts. Clearly, there's information about individuals, there's information about the relationships between individuals, about the inheritance relationships, there's information about the number of generations. And this then leads us to the second epistemic inquiry question of not just what exists, but how can we explain what we see in this existence? So how did those things happen? And that clearly is one of the key ideas in genetics. How the results of inheritance, how do they come about? What's our best model to explain them? So I think at this point, maybe this would be the start of a lesson after you've had the discussion about the phenomena of the family with the twins who appear to have phenotypic differences. And this would be a good opportunity to involve the concept of phenotype, because that seems to be the key in the history of genetics. Is phenotypes are shown in pedigree charts, and we use them as an inferential model to try to look at genotype and its inheritance. So this could be, okay, what exists here? And you might prompt how many generations, how many individuals, how many siblings, how many males, how many females. And at this point, I would just let students notice that the different coloration clearly is signifying some phenotypic difference that we're trying to illustrate. Then I think in a direct response to this, how do things happen, it's interesting to look at Mendel, and many people had the idea that what we see, and we do in some ways, see that inheritance is a blending of characteristics of the parents into their offspring. And this theory would be that distinctive variations might well be averaged out. So this was an idea that there would seem to be a lot of strong evidence for, and it was probably the common and most naive way of thinking about genetics. It still has quite good explanatory potential, but not complete. this would be a good opportunity to say, okay, again, what do you see and how do you evaluate it in relationship to the idea of blending? Already the students are familiar with this phenomena, and it might well be that some say, does these characteristics seem to show blending? Others might say, no, but they seem to be very particular, or they seem to be possessed by individuals and not others. So again, this is a good opportunity for you as teachers to discuss the kind of evidence this simple family tree of just 2 generations shows. And again, going back to what phenotypes are clearly genetic and what other phenomena or observable characteristics might be. Having used this with students, often leads to discussion, it's clearly not genetic that all of the males have short hair. They've had haircuts, haven't they? And that often is an interesting cognitive conflict that comes about because many focus on observable features. And again, if you say, how did things happen? Clearly, that's something that happened because of a choice, not a genetic inheritance. Then it's quite appropriate to continue this theme of what exists here, 2 generations, and there are different phenotypes, and does this give evidence for blending? And again, how do things happen? How do we go from these crossing of 2 very distinct phenotypes to get some kind of intermediate phenotype? I would not at this point out the concept of incomplete dominance. That can come later. Again, a second example. This is to provoke discussion about what evidence there is for a blending idea or model of inheritance or a particulate. And then this is extending then the idea that in science we often have to look at a longer term than just one set of observations and take into account a 3rd generation, for instance, which is exactly the kind of thinking that Mendel recorded. And again, taking all of this evidence, do you have to update your ideas? The students who would have been saying, there's great evidence for blending, now are confronted with something that doesn't quite fit in with that pattern of inheritance. Again, answering that question, how do things happen? Which model is the best model to explain how do these things happen? And then this is another example, similar discussions. I would tend to let the students see both of them and give them some time to develop, now do we have different evidence that supports blending or particulate model of inheritance? And this might be another example where we start moving to use the vocabulary of genotype, where we're saying, genotype seems to express what the particles of inheritance are. This was the kind of ideas that Mendel was formulating, that there was some particle that was passed on through generations. And that neatly leads into, to organize this, we introduced the model of Punnett squares. I would expect, of course, that you might well not follow what I'm showing you in this workshop, but you might intersperse some of these phenomena and their analysis and the questions of how things happen with some practice at other examples of pedigree charts, of phenotypes, and then starting to use the language of genotypes. And now it's probably a time to debrief about, the phenomena I've shown you and the logical steps I've shown you is not a lesson plan, it's a kind of series of agenda starters, and your students and you know your curriculum. So at what stage would you introduce the vocabulary, the practice, other examples, widening the scope of these two questions? What exists and how do things happen? The second phenomena that we are going to use to further students' understanding of genetics that we've covered with the Punnett squares and okay, moving on to our second phenomena, I'll explain a little bit about the background of our understanding of the evolution of domestic dogs and grey wolves, but in particular some examples of hybridization that have led to a very interesting phenomena, and there's lots of data about this that will help in the first steps of understanding to some of the factors that affect natural selection. It's a very accessible phenomena because effectively there are two major phenotypical variations, the lighter colour of the grey wolf and then the hybridized high melanin from the K locus. So the story effectively goes like this. At one time we did think that our domestic dogs were bred from Canis lupus, the grey wolf, but now there's evidence that the best explanation is that there was an extinct common ancestor of both of them, and that our domestication of this extinct wolf, that is a close relative of the grey wolf, started much earlier than we thought. There was a hypothesis that it was when humans had settled and so there's a lot of evidence of that, and that's then when we started domesticating wolves. However, recent findings have put the date back by many thousand, tens of thousands of years. So let's assume we don't know for certain, but that there's a common ancestor, which means that Canis familiaris, our domestic dog, is very, very genetically closely related to Canis lupus and also the coyote. And interestingly, this hybridized black wolf is far more common in North America than anywhere else in the world. There is some populations in northern Italy, but let's focus on the North American story. We believe, and again we have lots of archaeological and fossil and genetic evidence that humans moved into North America over some kind of land bridge from Asia, and many brought with them dogs that they had domesticated from the common ancestor wolf. So there's a higher population of domesticated dogs who are close to grey wolves in terms of their ability to reproduce. We know that that melanin is a major source of skin coloration, eye coloration, fur coloration in this sense. And so we have a phenotypic difference that there are some grey wolves that have very dark, almost black skin. And our genetic analysis says that this dominant allele is found at what's called the K locus on chromosome number 16 of wolf populations, of wolf individuals, and of domesticated dogs. So this is a good opportunity to teach things to do with what chromosomes are, what DNA is, what we mean by a locus, and the idea of the difference between genes and alleles. So these would be the kind of things that we traditionally teach, but to relate to this particular phenomena. Earlier in the previous section of this unit, we would have started teaching the idea of alleles of the way we show them with dominant large letters and recessive small. And here we need to really focus on the idea of sharing chromosome structure allows this hybridization to happen, and what a locus is and what can exist at a locus, which then enables us to come to know how things happen. All the genotypic data that we have seems to show that this heterozygous high melanin wolf is the dominant form of those black wolves. There seems to be some selection pressures against having the homozygous dominant. And we can look at the probabilities of mating between these and what the offspring balance would be. And that can become important later when we look at the geographical distribution and the proportions in the population of these high melanin wolves and the normal wild type grey wolf. What's interesting as well to point out in terms of how do we come to know how important DNA analysis is, because just field observations are confounded of this phenotype, as you can see. So again, I would ask you to discuss in your team and also think, what would students say? What do you notice that both of these genotypes have in common in relation to age, and why that can be a problem of actually identification in the wild? And we then need some forms of DNA analysis to be able to establish population numbers. A very interesting phenomena is that's happened recently in Yellowstone National Park with great ecological effects, very beneficial ecological effects, is Canadian wolves have been introduced into Yellowstone, and there's been an increase in their population. And this is work done looking at a pedigree chart. Again, you can ask students to interpret it, and it's a good forerunner to what's to come next when we start thinking about natural selective forces. This is the results of studies with DNA analysis in different parts of Canada, and the pie charts clearly show the dark wolves and their proportion out of the population, and the light or the wild type normal grey wolf. So what do you see? What do you infer? How would you try to explain how this has happened? And so also, what do you think your students would do? What would they need? Would you need to teach them the meaning of those pie charts, or just review that? And then when we go back to our original question, what exists is obviously dark wolves and normal wild type grey wolves, but we have other things that exist that we as scientists see, for instance, like changes over time, population distributions, climatic changes, vegetation changes, snow coverage. All of these are something that I would try to elicit from students just from the previous diagram to see what prior knowledge they have. But of course, we can scaffold and prompt them with some of these ideas. Then of course we can make it, first of all, more concrete in terms of picturing and giving them the knowledge of what tundra and taiga looks like, and what a boreal or coniferous forest will look like, and where they're more common. Then we have a beautiful temperature distribution for winter temperatures that maps very much onto this. And so this is a good opportunity to give students the opportunity to discuss what variables that they see, what relationships they see, what possible affects why the population distribution has come out as it is. Talk about camouflage, predation, all these kind of things. So again, we try to get together this idea of, okay, we know what exists, we have explaining to do, how did that happen? How do we come to know? Well, we're developing this model called the natural selective model. And so again, this could just be setting the agenda for much of the traditional teaching that you would do in giving them the knowledge to be able to answer these kind of questions. This is why it's called epistemic inquiry, because it's getting the inquiry started and setting out the parameters of what we need to know to answer these big questions, and how we can create some cognitive interest, cognitive conflict, and be able to bridge this to other examples in your curriculum of natural selective examples. So again, that's something that I think you need to look at, this phenomena, how it is used or can be used as a launch pad for your curriculum, for your students.